Let's talk about something fundamental to our modern world, the power generator. We're going to tackle a really interesting question today. Why does the voltage coming out of a huge power generator actually change depending on what we plug into it? It's a fascinating puzzle, and it's right at the heart of how our entire electrical grid works. You have absolutely seen this happen. You flip on the air conditioner or maybe the microwave, and for just a split second, the lights in the room dip. Well, that little flicker isn't a mistake. It's a real-world symptom of the exact thing we're going to break down. It's not a fault in your wiring, it's pure physics happening inside a generator hundreds of miles away.
So here's our game plan. First, we'll lay out the basic voltage puzzle. Then, we're going to decode the engineer's secret weapon for this stuff, the phasor diagram. After that, we'll look at 3 different kinds of things you can plug in, see how we actually measure the voltage change with a number, and finally, tie it all back to why this is so critical for keeping the lights on everywhere. Okay, let's dive right in. The whole issue, the core of this puzzle, is that there's a big difference between the voltage a generator creates on the inside and the voltage we can actually use on the outside.
Think of it this way. Deep inside the spinning heart of a generator, it's producing this perfect theoretical voltage. We're going to call that E. But by the time that power gets to the output terminals, the place you actually connect the wires, it's a slightly different voltage. We'll call that V. The mystery we're solving today is why E and V are almost never the same.
To really get what's going on, engineers use this brilliant tool called a phasor diagram. Now, I know it might look a little abstract and kind of complicated at first, but trust me, it's just a map. It's a visual way to see all the different electrical forces that are in play.
So on our map, the very first landmark is V, the terminal voltage. This is our ground truth, our "you are here" dot. It's the voltage you could literally measure with a voltmeter right at the generator's output. We always draw it as this flat horizontal line, and it becomes our baseline for everything else.
Okay, next up is the armature current, which we'll call I sub A. This is the actual flow of electricity going out to power something, a factory, your house, whatever. But here is the absolute key. The angle of this current, compared to our voltage V, changes depending on what kind of device it's powering. And that angle, well, that changes everything.
And finally, we get to E, the excitation voltage. This is the one we've been talking about, the generator's pure, perfect internal voltage, before any losses happen. By mapping out where V and I sub A are, we can figure out where E should be. And the difference in the length of the line for E and the line for V, well, that tells us the whole story.
Now for the really cool part. We get to see how this entire picture, this whole map, changes completely based on what you plug in. Let's look at 3 totally different situations.
First up, a lagging load. This is for anything with a motor, like that air conditioner we talked about. Now, don't worry about all the crazy angles here, just focus on the length of the lines. Look how the line for V, our real voltage, is noticeably shorter than the line for E, the ideal one. That gap right there represents a pretty big voltage drop. This is literally why your lights dim. Okay, next, what about a simple device, like an electric heater? That's what we call a unity load. If you look at this diagram, you can see V is still a little bit shorter than E, but the difference is way smaller than it was for the motor. The voltage still drops, but it's much less severe.
And finally, we have the real weirdo of the group, the leading load. You don't see this much in homes, but it's used in industry. Now check this out. In this scenario, the final voltage V is actually longer than the internal voltage E. That's not a typo. The voltage at the output is higher than what the generator was theoretically making inside. How wild is that?
So, let's just nail this down. The big takeaway is this. Motors cause a big voltage drop. Simple stuff like heaters, they cause a small voltage drop. And these special industrial things called capacitor banks can actually cause a voltage rise. It all comes down to the personality of the load you connect to the generator.
Seeing this on a diagram is one thing, but for the engineers who run the power grid, they can't just eyeball it. They need to put a hard, precise number on this effect. They have to measure it.
And this is the tool they use. It's a formula for something called voltage regulation, or just VR for short. This pretty simple equation lets them quantify exactly how much that voltage is changing when a load gets connected.
So what is voltage regulation, really? It's just the percentage change of that terminal voltage when you go from having nothing plugged in to having it running at full power. To put it even simpler, it's just a number that tells you how much the voltage sags when it's under pressure. And when it comes to VR, a lower number is always better.
A generator with a low voltage regulation, say 2%, is rock solid. Its voltage barely budges. But a generator with a high VR, like 10%, that one's going to be a lot less stable. Its voltage is going to sag a whole lot more when you connect something big to it.
All right, so we've gone from dimming lights to these phasor diagrams to formulas. Let's zoom all the way out now to the big picture. Why does managing all this stuff matter so much?
It matters because a rock-solid stable voltage isn't just a nice-to-have feature. It is the absolute foundation of a reliable power grid. Our entire high-tech society completely depends on it. It's totally non-negotiable.
I mean, think about it. Good voltage regulation is what protects your expensive laptop and TV from getting fried by voltage swings. It's what prevents constant flickering lights and brownouts in your neighborhood. And on the grandest scale, it allows giant industrial machines to run smoothly and keeps the entire power grid perfectly synchronized and stable.
And that kind of brings us to one last thought. This voltage puzzle, engineers have been working on it for over a century. But now, as we're adding millions of totally new and complex things to the grid, I'm talking electric vehicle chargers, huge solar farms, managing this voltage regulation is getting way more complicated and honestly more important than ever before. Solving that puzzle is going to be the key to building the grid of the future.